Hi, I'm Wayne Lack and I'm doing January 2013 Core 3 AQA paper. I'm now on question 8, which happens to be the last question of this paper. They always try to end maths papers in general with a horrible question, whether it's masked up to be something horrible or it's just really mean things that you can easily trip upon, or lots of marking points. They tend to end on something quite hard, and that's reflected here with my examiner's report. Part A, quite a bit of confusion in that one actually. We'll talk about that in a minute when we turn to the whiteboard, but an average amount of students managed to gain full marks, but it wasn't as pro as the rest of the questions. And Part B proved difficult for even the most abled students of that year. It was quite a difficult question. If you really think you know one thing, that's not enough for this last question. They mix up lots of things. So let's turn to the whiteboard and do question 8. So 8A. B was particularly massive, so I'm going to have to do them on separate boards. So A, show that the integral of e to the power of 1 minus 2x by dx between the points natural log 2 and 0 equals 3 over 8e. So our first step clearly is going to be to integrate the e to the 1 minus 2x. So a reminder, if you have e to the ax, if you integrate it, that equals 1 over a e to the ax. Now, if what we have is e to the 1 minus 2x. So the only thing in front of an x here is this minus 2. And we actually sort of ignore this 1. We ignore the 1 entirely for this, and we just divide by minus 2. Some people divided by 1 minus 2. That isn't quite right. What a few people did is they let u equal 1 minus 2x. Then they used the chain rule in differentiation and differentiated it rather than integrating. That's not quite right either. So if you integrate that with respect to x, what we actually get is minus a half, because we've divided by this minus 2, we've got 1 over minus 2, which is minus a half, e to the power of 1 minus 2x. So that's what we get if we integrate e to the power of 1 minus 2x. Now that we've done that, we need to do what we normally do for integration, and do it between the 2 points. So first we put in minus a half e to the 1 minus 2 lots of natural log 2. And then we minus the other bracket, which is minus a half e to the 1 minus 2 lots of 0. So this bracket is going to be easy. We can deal with that in a minute. This bracket is where there's going to be errors, or more likely to be errors. So firstly, we're using a natural log rule. We have this 2 natural log 2, which we can write as natural log 2 to the power of 2, which is natural log 4. So that's the first rule we need to bring in. So that makes this bracket minus a half e to the 1 minus natural log 4. That tidies it up just that little bit more. It makes it easy to deal with. But that requires you to know your natural log rules. So now comes another rule of how to break up this e to the power of 1 minus natural log 4. So what I'm going to do first, I'm going to switch it round to make it minus natural log 4 plus 1. And what it becomes is we've got this minus a half, and then we'll have e to the negative natural log 4, so I've just swapped them around. Then we'll have e to the 1. Now that requires you know your rules about exponentials, because what some people did is they broke it up and put this minus in between it. So they said that is the same as minus a half and then a bracket e to the 1 minus e to the ln 4, and that's not the same. That's not how you break up these exponential things. Then we need to know what happens if you have an exponential to the power of a natural log of something. So if we have an example, we had e to the natural log of 2. The e and the natural log cancel out to make 2. But this time there's a minus, and when you've got something to the power of a minus number, that means 1 over the thing. So in this case we'll have this minus a half, that stays. But then the e and the log will cancel, but instead of giving 4, it will give a quarter, so 1 over 4. Because of this minus, it means 1 over. And the e and the log do still cancel out to give you this quarter. And then we've still got e to the 1 is just e, so I'm just going to write e. But you wouldn't be penalised for putting e to the 1 either. Both are fine. And then finally, now that we've done all these silly little rules that people forget, we can bring down what we had up here, all the way down here, which is going to be minus a half, and it's going to be e to the 1, because this 2 times 0 is 0, so it's just e to the 1, so a half e. So, what is that? Well, minus a half times minus a quarter is minus 1/8 e, minus, be careful of your minuses, we've now got minus, but let's put it in terms of eighths so that we'll be able to apply it to this one. 1/2 is the same as 4/8 e. So now if we've got this minus, that's going to be plus. So we've got minus 1/8 plus 4/8, which is positive 3/8 amounts of e, which is what we wanted in the question. Altogether, this was worth 4 marks. Now it requires you know your natural log rules there, how to break up your e rules here, how to integrate the whole thing at the beginning there, and getting to an answer as a proof. Because what some people did is they did all of this right, the hard stuff, then they got this minus 1/8 e minus 4/8 e, they typed that into the calculator, they got a decimal, they wrote down the decimal and said that decimal equals 3/8 e. And that's not what they want for these sorts of things. They want you to get to the answer 3/8 e, not as a decimal but as 3/8 e, to show it exactly, to show that that does exactly equal that. So this required you to know a few rules, but let's go on to part B, because that's where most marks were lost. So part B, the grand finale of this paper. Use the substitution u equals tan x to find the exact value of the integral of sec to the 4x root tan x by dx between pi over 4 and 0. So being the last question of the exam, they're going to try and throw in a few things there. So it's going to be quite a lengthy process, quite a few things you could trip up on as a last question. So firstly, what we've got here, this thing we're going to integrate eventually, let's see if we can simplify it and put it in terms of u. That's always a good start. So this sec to the 4x means nothing to anyone, really. Sec to the 4, we don't know any rules for that. But hopefully you can see that that quite neatly becomes sec squared x, which you are familiar with, squared, root 10x. So that's the first thing. That's simplified it a little bit, because it just so happens that sec squared x equals tan squared x plus 1. It just so happens. And hopefully you'd know that rule off the top of your head. If you didn't, then this question would prove particularly tricky. So sec squared x equals tan squared x plus 1. So we can therefore write this as tan squared x plus 1 squared root tan x. We can do that. Now we've got this u up here, which is tan x. Let's not forget that. So tan squared x therefore must be u squared plus 1, which is just 1, you can't write that in terms of u, squared, root, and tan x is u, so it becomes root u. So all of this is now our integral with respect to x. So we don't want to integrate it with respect to x, so I haven't bothered writing on our parameter things yet, because we don't know what they're going to be in terms of u yet, so we're just going to ignore that. We're differentiating with respect, or integrating with respect to x at the minute. We don't want to do that. So it's told us what substitution to use. We've got u equals tan x. u equals tan x. Therefore, du by dx, you just should know how to do this, sec squared x. When you differentiate tan x, you get sec squared x, and that counts on the fact that you know that. So if we rearrange this to get it in terms of dx, so what does dx equal? It's 1 over this sec squared x du. So that's how we would do that, because dx would be du over sec squared x, which is no use to us, we want it in terms of du on this side. So it's 1 over sec squared x du. So dx equals, now this 1 over sec squared x, we've just had to change a sec squared x for our tan. So we changed it into tan squared x plus 1. So we change this one just like we did for that, it becomes u squared plus 1. This time it isn't squared because it was squared here because it's sec to the 4, whereas this time it's not, so that's du. So to get this whole integral in terms of u, we have the integral of u squared plus 1 squared, square root of u, but then dx is now replaced with this 1 over u squared plus 1 du. And when you times that out, all of this bit is going to be the numerator, and then this will be the denominator. So one of these u squared plus 1 can cancel with one of this u squared plus 1. So completely get rid of a fraction and take this from squared down to just a single u squared plus 1. So we're going to be integrating u squared plus 1 lots of root u with respect to u. So if we're integrating with respect to u, we then have to change our parameter things, these numbers and the integration sign, I've forgotten what they're called. Let's call them parameters for now. So we've got u equals tan x. Well, I'm going to re-remind you, I know I've wrote it there and there, I'm going to re-remind you here. Because now what we need to do is find out what these values are, because these are with respect to x, these two values. And we want them now with respect to u. So if we put them into here, in place of x, then we'll find out what they are in the place of, in terms of u. So we'll have u equals tan pi over 4. So that means u equals, and you could type that into your calculator, tan of pi over 4 is 1. So that's our new upper parameter, 1. And if you do tan of 0, that gives u to be 0. So this 0 is still 0 down the bottom. So now we're integrating u squared plus 1 times root u by du in between the points 1 and 0. So the next step would be to expand out these brackets to get a nice term. So integrating between 1 and 0. Now this is where your rules from core 2 come in. U squared times root u. Root u is u to the half. So when you times them together, you add the powers. So you've got 2 plus a half, which is u to the power of 5 over 2, plus u to the half when we expand 1 times root u by du. So that's that. So now we can actually integrate that. So what we do is we add 1 to the power, we'll get u to the 7 over 2, and then we divide by 7 over 2, so it's 1 over 7 over 2, which is 2 sevenths, plus, then we add 1 to the power here, so we're going to get u to the 3 over 2, then we divide by that, so it becomes 2 over 3, u to the 3 over 2. So then we put in our two values, so we get 2 sevenths, lots of 1 to the 7 over 2, plus 2 thirds, lots of 1 to the 3 over 2, minus, and then you swap them all for naught, so we get 2 sevenths naught to the 7 over 2, plus 2 thirds naught to the 3 over 2. That's supposed to be a rounded bracket there. So this bracket is all going to become 0. It's going to be minus 0. This bracket, 1 to the power of anything is 1. So it's going to be 2/7 plus 2/3. So we need to get them in terms of each other, and the lowest common factor of 7 and 3 is 21. So that's the same as in terms of over 21. We get 6 over 21, because we have to times it by 3, plus 14 over 21, which is 20 over 21 as an exact value. You wouldn't do that to a decimal because it says an exact value up here. So let's quickly go over everything we did very quickly. So we got the whole thing in terms of u where possible. We simplified the sec to the 4 to the sec squared x squared. We got it all in terms of u. We had to remember the rules sec squared x equals tan squared x plus 1. We then knew u equals tan x, so we did du by dx. We found out what dx equals, so we can substitute it back into here, so it's entirely in terms of u. We then simplified that down a little bit to get to a thing we could actually integrate easily. We then integrated it using core 2 rules, that's nothing new. And then you use the rest of your rules just like you did in core 1 and core 2, where you just bunk in your numbers, but we had to change our boundaries from x to u, and then we got a final answer. And this altogether was worth a whopping 8 marks. What a way to end a paper. If you know what you're doing, that's 8 marks at the end of a paper to make you leave that exam hall really happy. Now, of course, if you don't know what you're doing, well, watch more of my videos and you will. So hopefully this helped. That was question 8, but that's the last of the paper. So altogether this has been January 2013. Hope it helped a little bit, and I'm going to do June 2012 next, so see you there.